Welcome back to Maths with Mrs. J. We've been talking about graphing functions using stationary points to help us get the shape of the function. Now we're at a point where we can actually use our information about finding stationary points to work out some everyday life situations. Now, probably the most basic maximum minimum problem that you will come across in pretty much every textbook is going to be something to do with what I've got here. So we're finding the dimensions of a rectangle that's got a set perimeter. In this case, our perimeter is 1,000 meters, and we want to make the area of the rectangle a maximum. So a situation like this could be something like a farmer has a certain amount of fencing, wants to build a paddock to keep his or her sheep, and obviously for that amount of fencing you want to get the maximum grazing area. Now, I've said to you before, when you're going to do a diagram, I know we want to save the planet, but please make it big enough so that you can write in any information that you're going to need to write. Now, it's a rectangle, obviously. Let's start by labelling the width and the length. You can use W and L, it's up to you exactly what you want to do. Because we've introduced some variables, we should literally introduce them. So we should say something like, let X meters be width, and let Y meters be the length. All right, so if whenever you're going to introduce an X or a Y or whatever, you should actually define that variable. Now, there will always be, at this stage of your calculus anyway, there will always be some information either in the question or that you can work out some other way, maybe using Pythagoras or a diagram or whatever, that will enable you to find a relationship between your X and your Y. Because at high school level, you only can do calculus in one variable. You don't do multivariate calculus usually until you're at university level. All right, what do we know? What are we told in the question? Well, we're told that the perimeter is 1,000 meters. What do we know about perimeter of a rectangle? Well, we know that perimeter is our 1,000 meters. And we know that our perimeter is our 2 times our length plus width, which is our X plus Y. Let's move up here. So obviously X plus Y is going to be 500, dividing both sides by 2. So if we put Y in terms of X, Y is obviously going to be 500 minus X. I'm going to call that equation 1. So that's using information in the question, or perhaps some geometry, depends on the question. In this case, it gave us the perimeter, to get one of the variables in terms of the other, so that now you can only work with just the one. All right, now what are we maximising? It wants us to maximise the area. Let's get an expression for the area of this rectangle. Area is length times width, which is X times Y, which of course is X times 500 minus X, which when we expand, we're going to get 500X minus X squared. So this now, at this point, has become our function that we're going to maximise. We should have a bit of a look at this function for two reasons. It's helpful to know what sort of function we're dealing with, and it's also helpful, we need to know what the domain is. In other words, what are the possible values of X that we can have? Now, you should be able to tell from here, Y is 500 minus X. So clearly, X has to be less than 500, doesn't it? Otherwise, we'd have a negative length and it's just not going to work. Also, x being a length has to be bigger than 0. So we should put our domain here. We should also think about what sort of function this is. This is a quadratic function with a negative x squared term. So it's going to look like that when we graph it. So our local maximum that we find will actually be the absolute maximum. We're quite lucky with quadratic like that. If we had something like a cubic function or something more complicated than that, we might find a maximum there, we might find a maximum there, and we've got to work out which one's more, etc. We might even have something coming up to here, and it might be at the end of our domain that the absolute maximum is what we need to take for that smallest value of x. So just bear that in mind. Get rid of that. Okay, all right. So now we're at the point of maximising and minimising this. We're trying to maximise it. So we're going to do dA dx. Is going to be 500 minus 2x. For a stationary point, we're going to put that equal to 0. So 500 minus 2x is 0. So 2x is 500. So x is 250. All right. So now, when x is 250, what is y? Well, if we sub it into here, we get y as 250. Does that work? Well, yes. 250, 250, 250, 250 gives you your 1,000. What have we got? We've got a square. Now, we can just check the endpoints. The endpoints, you're actually going to get 0 as your area. We should prove, I guess, we know that because this is a negative x squared term, that will be a maximum, but let's just do our second derivative. Is going to be -2, which is negative, so it's concave down, so it's a local maximum. Now, because we've been asked our question in the form of a sentence, we should answer in the form of a sentence. So we should say something like, therefore, dimensions should be 250 metres by 250 metres. You could put in brackets that that's a square.